lesson-only mode.
Okay, welcome everybody to follow the webinar about the torsional warping. And a few practical things before we start. So this is a live event, so it means that if you have any questions, you can press the raise hand button, and I will try to answer with my best. But there's plenty of people today at the webinar, so if I don't have time to answer all of your questions, I promise to answer them individually after the webinar. So now we are talking about torsional warping, but few examples what they have done lately. So in our software FEM-Design in version 22, we did time-dependent construction stage analysis, and in version 23, we did a material nonlinear model for concrete and steel. And last year, we modified the material model and did thickness-wise plasticity to steel and a few modifications to concrete nonlinear model. So there has been always, like every year, something minor finite element development going on. So, and this year is not an exception. So in this year, we develop a 7 degree of freedom beam model, and we're gonna talk about that today. So we start with a few. I put it intentionally in the beginning that there are few misconceptions about torsional warping, and we look those first. So it's very common to think that 7 degree of freedom is some kind of high-tech feature only for the best users, and also that 7 degree of freedom is only for lateral stability of the beams, like high I-beams and portal frames. But that is not true. It's a 7 degree of freedom is mostly for like simple structures, and probably everyone who is using beam models in some way. So it's important, and it's more general than usually people think. So if we take an easy example to understand, so we want to design this support beam, and this would be like structure usually given to like beginner. So it's a really simple structure. We want to design the beam here, and then we do it with the two specific models. We have a 7 degree of freedom beam model, and we have a classical beam model which has 6 degrees of freedom. And then we calculate the deformations, and we can see that the deformations are a bit less with the 7 degree of freedom beam model. And if we compare the deformations with the reality, what is now the solid finite element model here, we can see that actually the 7 degree of freedom beam model is much closer to the reality. So it doesn't have to be very complex structure to use 7 degree of freedom when it comes like really necessity to use, as this example shows. So you can see that this 7 degree of freedom beam model is much more realistic in this case. And if we look the stresses of the same model, we can see that if you look the cross beam stresses, the classical beam model cannot predict these high flange stresses of the beam, but 7 degree of freedom beam model, as what is this above model, matches pretty closely to the solid model, even with the short spans, because we are using general method here. And stresses are a bit off with the classical beam model. So it doesn't have to be complex structure. It can be simple as crane beam. Also crane beam design requires 7 degrees of freedom to calculate them correctly because of the location of the wheel load. So it's not like exotic big structures are demanding. It's like everyday structures mostly, or like everyday designers who need this feature. And the reason why we do finite element analysis in the first place is that we want to connect element together with the right stiffness. And that's what 7 degrees of freedom is about, that we get the right stiffness of finite elements between the elements. So 6 degrees of beam model does not have enough degrees of freedom to describe all of what's happening in the real world. So it's just basically that what the 7 degree of freedom beam model is, that it's like a fixed to classical beam model, which makes beams more realistic and gives them right stiffness in the finite elements. And of course, we get those like fancy looking stability modes, lateral torsional buckling and combined stability modes. So it's like a byproduct when we add this new thing to our beam models that we also get those. But that is not the main reason. Main reason is that we get the right stiffness to finite elements. Also, 7-degree of freedom is often advertised that it's a steel feature, that it's only for thin-walled steel sections. But in reality, it doesn't work like that. Here we have an example of a concrete building, and we have a building core, what we have modeled as a beam model. And we can see clearly that there's a warping going on in the core. And if we turn on the warping, we can see that the stresses increase, and same here. We have a closed section, and still warping increases the stresses. So warping is pretty much property of all of the section shapes and all materials. So it's nothing to do with the steel, basically. It's just a cross-section property. Okay, then I want to explain how torsional warping really works. So I explain it so that you don't have to know anything beforehand. Only if you have used beam models, then that is enough, like the background knowledge here, to understand how it works. So let's dive in. So we take a really simple example here, which this cantilever beam. We have a bolted connection on the one end, and then we apply torsional bending moment to beam, what is illustrated here with this point load with the cantilever on the end of the beam. And this is the solid finite element model, so you can see what happens. So this is roughly what's going on. So the beam will rotate as expected. And if we calculate it with the classical beam model, we roughly get about the same rotation as the solid model. So where's the problem then? Okay, let's look closely what happens. And even if the stresses they match with the classical beam model really well with this case. So what is this case? This case is actually what is called free torsion. So it means that the flanges can move freely in the support or the beam direction. And here, like classical 6 degrees of freedom beam model works really well. It's really close to what happens in reality. But the problem basically is that this is really like seldom case or rare case in reality. So most of the beams they are like partly prevented or fully prevented. So this stress state where we twist the beam and what the 6 degrees of freedom beam model, third degree of freedom, describes is called St. Venant torsion, and it's basically torsion what is carried by the shear of the section walls. And if you have two types of sections, you have closed sections and you have open sections. For the closed sections, you have this kind of shear distribution when there's like a shear going in one way in one wall and opposite direction in the other side of the wall. And with the tubes, it's like a constant shear flow along the wall, and in the opposite side of the profile, it's on the other direction. And if you look at it in the 3D, this is actually what's going on. It might be easier to understand. So there's actually compression and tension in the wall, and they are like 45-degree angle to each other. And if you look on the other side, they are actually, the magnitudes are the same, but they are like, the signs are different. So the compression in this way, this side, and this opposite on the other side. But if you look the tube, there's the compression and tension vectors are in the same direction on one side of the tube, and they are like opposite in this side. So this will explain why the torsional stiffness is so high in these closed sections. It can be like 10 to 100 times higher than the open sections. But this will come handy if you think this as a two principal stresses when you think about the shell models and how warping or St. Venant works in shell models. And it's described easily if it's a shear related, so it's just proportional to shear modulus and torsional stiffness of cross section and angle of twist. So it's really simple to describe with this equation. So we do a bit modification to our beam model. So let's add a friction of the bolts and preload of the bolts to the model and see what happens. And if you look the mid of the beam here, you can see that there's actually same exact torsion flowing through the beam. But if you look at the stresses, they are a bit different if we modify the boundary conditions of the beam. So in reality, it's seldom that we have this like free torsion. It's like a really weird case in reality. So usually it's like partly prevented or fully prevented torsion in reality. Even with these, like you would think that there's a beam in the web that this is not prevented, but in reality it is. And if you do a modification to the model, so we put a really thick flange in the beam, you can see that now the stresses are totally different. So if you look this side, you can see the same torsion flows through the center of the beam or mid of the beam, and the stress state, how they are carried in the beam, is totally different if you put the flange. So the exact same external forces causes totally different stresses if you prevent the flange movement. And same applies to translations or displacements. It's 30 millimeters here, and if we prevent the flange movement, it's 11 millimeters. So it's or 12 millimeters, but anyway, it's a 1/3 of the deformations. So in this case, the beam model will give like 3x mistake, or the stiffness is 3 times too low. So we really need like the 7 degree of freedom beam model here. And if you see what happens, there's a warping going on, and this is a 6 degrees of freedom beam model. So it's commonly people think that 6 degrees of freedom beam models do not twist, but or warp. They actually warp. So it means that the warping change is constant along the beam. That's what's going on. So the warping can happen freely. Let's look the degrees of freedom of the beam model so you understand better what the warping is. So here's the first degree of, or like a tension of the beam, and shear of the beam, or vertical shear of the beam, or twist. So this is the St. Venant part. And then we have a bending. Of course, you probably know all of these first 6, but this is what the warping looks like. So it's like a movement of the flanges to the opposite direction, if you think about this as an I-beam. And the total stress states of the beam, it's really complex. It looks something like this, but if we divide it into 2 components, so we have a component what is St. Venant, and then we have another component that is like the warping. And if you now look the warping component, it's like really clear what's going on. So it's basically you probably guess what this thing is. That it's like bending of the flanges. So total torsion is carried by 2 mechanisms in prevented torsion. So it's a St. Venant, and then there's a warping. And if you look the warping closely, you can see, it's hardly to see, but now if we divide it to bending of the flanges, it's more clear what happens. So it's basically like a classical bending theory. If you want to calculate yourself, you can calculate it as a bending theory, but this is not same as a general warping, because this theory has limitations, and we will discuss them later. But if you apply your classical beam bending theory to flanges, you roughly get the idea what happens when you twist the beam, and what warping really is. And if you replace the displacement of the flange with the rotation of the beam, so we get the equations of warping. But this is way too simplified theory, but this is basically how warping is explained as a bending theory. But this is not what we have applied to software. This is like simplified explanation. And there's a warping stiffness, which is basically just the bending stiffness of the flange, or flange bending stiffness multiplied by the height to the second divided by 2. So it's really easy. And also there's our equation. So you can see that it's a third derivative of beam twist, because it's a bending related phenomenon, and St. Venant is most like shear governed phenomenon. So it's a bit different. It's only like related directly to the beam twist. So they change a bit differently. But if you think it like as a flange bending caused by the torsion, so it might be easier to understand. So this is just like mental model for you. If you start to think what warping is, it's a bending of flanges. And then we need a new internal force, because now we have a new degree of freedom, and the new internal force for warping is Y moment. So you can think it as 2 opposing moments, and they are separated with the height. And the unit is kilonewton meters squared, because we have this height property. And we did this height because the different beams are different height. So we always get the Y moment, and those bending moments has to be equal. But bear in mind, this only works with the I-beams, and in reality, there's a multitude of shapes and thick sections and so on. So this is just like, if you want to think it as a two opposing moments, this is the like best you can understand. But in reality, like the beams has ultimate many flanges in height direction. So, but for I-beams, this theory will work like pretty well, that you think it as a bending of flanges. But in reality, the bi-moment affects in every layer in the beam height direction, and also the other axis. So it's not just like horizontal; it also bends in the vertical direction if you have a more complex section. But if you think it as a bending theory, you can probably inspect even your 7-degree of freedom model. So if you think that the wall thicknesses in this beam is really thin, so then the bi-moment shapes would be like really close to the bending theory. So what would you guess what is the right bending moment shape if you think that this twist will cause bending of the flanges? So is it A, B, or C? And okay, I will reveal the answer. So the C was the correct answer. So yes, is the bi-moment shape of this cantilever system. So we draw beam and take out the bi-moment. So it's basically just like cantilever. It bends the top flange to the right and bottom flange to the left, and it's a cantilever for those. And if we do another example here, we have a surface area load, and it's not located in the center line of the beam. And in this example, we will assume that it's free to rotate over this concrete wall. So what is your best guess? What is the bi-moment shape for this system? Okay, let's do it in our software, and the shape is this one. And if you guess it that it would be B, you would be correct, because the support moment has to be like twice the height of the span moment, because it's a bending theory, and you can see the bi-moment is twice the height here in the support, close to support. But yeah, you can somehow, if you want to inspect those like 7-degree of freedom models, it's handy that at least for the I-beams you can calculate something. But in reality, there's ultimate many flanges and bi-moment effects on all of those beam layers and around both axes. And here's the example if you bolt it down over the concrete fall. So it cannot rotate, and then the bi-moment shape would be something like this. So you can inspect that your model works so. So mixed torsion means that there's like two different mechanisms carrying the torsion, and it's a Saint Venant, the classical shear of the walls, and the bending of the flanges or the warping. And it depends on the boundary conditions of the 7-degree of freedom and MX boundary conditions, and also because one is related to shear and other is related to bending, so they change in the different rate in the beam. So it's really complex how they change between these two mechanisms in the beam. So we go back to the original question or the misconception. So solid sections you can warp, but the warping effects are much more local. So actually, like the circle is only one we can really safely say that it do not warp. So all the other shapes has the warping function. So it means that they warp more or less. So if we take an example, and I call it this effect as a decay of bi-moment. So it means that the bi-moment decays fast if you go away from the support. So here we have a concrete beam. We have applied the torsion to the end of the beam, and we have fixed the movement of the, let's say, flanges. There's not flanges in this system, but we can call that the flanges are fixed, so it's casted to some massive concrete structure. And we set the fixed warping support here. And then we observe the bi-moment, and bi-moment decays fast because the torsion or Saint Venant thickness is incredibly high in this solid section. But still there's local bi-moments. And if you look the Saint Venant part, you can see that it drops just a bit here close to the support. So we can say that most of the torsion effect comes from the Saint Venant, but the bi-moment still has a little effect in this section. So there's no any absolute limits when the warping can be neglected. There's always there, and if you have a general model, you can take it into account. And maybe we take a more practical example. So there's a concrete attached to, so it's a beam model attached to shell model. And because the shell models only have 5 degrees of freedom, we need warping support in here. And let's see what happens. So there's a cantilever, concrete cantilever here, and we can see that there's significant bi-moments in the model, because we have a warping support here, and then we have a torsion in this section. So there's local bi-moments happening in the concrete. And if you look at the stresses, the 6 degrees of freedom beam model give you this stress distribution, and if you look the general 7 degree of freedom beam model, we can see that the stress is almost double. But this is just, if you look there globally, you can see that the Saint Venant works really well, but in close to the support, only the bi-moments start to change the stress state of the beams. So globally, this is like the 6 degrees of freedom is okay, but locally, we can say that the 7 degree of freedom beam model is more accurate in this case. Then we have another thing when you start to use these 7 degree of freedom beam models, and this is really complex, but this you will face almost immediately that this is, and if you have used the classical beam moments, this is like so against your like what you have learned in the school and what you know about the beam theory. So let's apply this torsion in the middle of the beam. So there's a 1 kilonewton load in the middle of the beam, and let's see what happens. And this is what happens with the 6 degrees of freedom. There's a lot of torsion in the beginning of the beam, and the rest of the beam is like stress-free. But if we observe what happens in reality, this is not even close. So if you look at the stresses in the first part of the beam and second part of the beam, you can see that they are almost equal. And we have a lot of stresses in here. Only just the end of the beam, there's like in this corner, you have like 0 stresses, but you can see how like totally off the 6 degrees of freedom beam model is in this case. So there should be a lot of stresses in this part of the beam. But if you use the 7 degree of freedom beam model, so this is a 6 degrees of freedom, and this is a 7 degree of freedom beam model. So now it matches what we can observe in reality. And what happens actually if you think it as a flange bending? First, the flange bends to the left and right, but they cannot snap back to the original shape. So they slowly decay or return to original shape, so the twisting returns. And if you look like the Saint Venant and torsional warping, in the beginning they are same sign, but here they have an opposite sign, and they cancel each other out perfectly. So we have internal stresses without any external loads in this part of the beam, and it matches the reality. It's really complex, but unfortunately that is like nature, how torsion works, and 7 degree of freedom can replicate this really well. Another benefit of 7 degree of freedom is that if we have these unsymmetrical sections, there's always dilemma in the 6 degrees of freedom beam models because they assume that you place the load in the shear center. But in reality, shear center is here. So if you place the load here, you don't have any support reaction or the torsional reaction, this green vector, rotation vector here, it's 0. But in reality, if you place it on the shear center, then you should have like a reaction here. So load cannot be located in 2 places simultaneously. So these do not work in the classical beam theory. But if you apply the warping or 7 degree of freedom, it works perfectly. So you can define the location of the load and the problem is solved. And the other thing is if you have like unsymmetrical flanges of beams, this is what happens. So first we observe the reality, and then we see how much is the deformations with the 6 degrees of freedom classical beam model. So they are totally off. It's 8 millimeters is the right solution, and a classical beam model gives you 41 millimeters or 42. So it's almost like 4 times too high or 5 times too high. And if we switch to the 7 degree of freedom beam model, they are almost spot on with the reality. If you look what happens, and they are really short span. So actually we need general 7 degree of freedom, but we will discuss later how it works. And also one thing happens if you apply the same bi moment to the top flange and bottom flange. What happens? This will bend more, this bottom flange, and the center of gravity of the beam has to move sideways. And that's also happening with the 7 degree of freedom beam model. So the center of gravity of the beam moves left, and same here, and almost like 0.8 millimeters, same magnitude. So it matches the reality pretty well. But in 6 degrees of freedom beam models, if you twist them, the beam doesn't move sideways. Or if you prevent the movement of the center of gravity, there's stresses introduced in the beam. So also in these cases, when you have like twist and unsymmetrical section, the 7 degree of freedom beam models are really handy. Then if you think what kind of finite element models we can describe warping, the solids, of course, they work perfectly because they can describe everything, but also shell models work really well. So shell models matches the stress-wise. If you compare the stresses of shells and solids together, they are pretty close to each other. But what is the weakness of shell models? are these local peaks what shell model cannot predict. So there's a lot of if you twist the beam, there's not a peak value. And if you look the cells, the mx or bending moment is 0. Also the other bending is 0. But what happens, the twisting of the beam manifests itself as a mxy bending of the shells, and that's what shells have. And that is like the stress states where you have the compression tension opposite directions in opposite sides of the shell. So that's actually mxy. And of course, if you have a 7 degree of freedom or 6 degrees of freedom beam model, that works like really well. So here we do not need, but if you have this warping, then we really need those 7 degree freedom beam models. And now we can use all of these. We can use solid, we can use thick shell theory, or we can use beams, and they all equal pretty well or match each other. So just like the classical beam twist, you can use 6 degrees of freedom. But in general, if you have anything, then it's a 7 degree of freedom is like really comparable to thick shells and solids. Okay, then we discuss about our theory, the general 7 degree of freedom, how it works and how it's different than the other 7 degree of freedom theories there is. And first, I want to thank you, our finite element developers. So they are the Sultans who have, and they have written really well, like theory manual, almost 100 pages long. So if you can want to know more, I highly recommend that you read it. You can find it on our website. But anyway, it's a good and it has a lot of like the theory examples about this theory. So we start with the Vlassov, and this is probably what if you have used finite element software, what has the 7 degree of freedom, this is probably the theory you have been using. And it compares to the Bernoulli beam theory. And it means that the Bernoulli beam theory, there's no any shear deformations in the beams. So if the beam is getting shorter and shorter, you get a bit like error in your calculations. And if you have like a half meter long beam with the flanges 200 millimeters wide, you can almost like 10% of the exact solution. So Vlassov warping theory does not allow thick walls, so it's only for thin walls, and it's only for open sections because the shear component of the warping is missing there. So the warping doesn't cause any shear deformations, and the warping doesn't increase because of the shear deformations. But the problem is that most of the finite element softwares anyways use Timoshenko beam models. So in Timoshenko, there's a shear deformations in the beam. So it means that also the shear deformation is taken into account. So there's like a contradiction between the warping theory and the bending theory and the normal beam theory. So, but it's easy to calculate, as you see, with the bending theory, and easy to formulate. So that's like the benefit. So basically, it just means that the warping is only explained by the bending of flanges or bending of beam fibers. Then we have a Kolbrunner, which is more complete theory, and this is like the basics of theory what we have applied to software, and it takes also the shear stiffness into account. And it's comparable to Timoshenko beam theory, so it means that if we apply this theory, then we are fully compatible with our normal beam model. And it's also suited for short beams, so there's not this weakness that if the beam is getting shorter, you are not causing any error in the calculation. Also, if you have a statically undetermined system, it's really important that you use Kolbrunner then. But we assume in the Kolbrunner that the shear is constant, or we approximate parabolic stress distribution in the walls. So it only applies to thin walled sections, because in complex 3D shaped sections or 2D shaped sections, we don't know the shear distribution in the section. But the good side here is that we can also use it to the closed sections. And then it's our theory. So it's basically based on the Kolbrunner, but now we don't have any shape limitations because first we assume that our warping function is first order. So it means that we assume this shear stress to be constant, what the warping causes. But in reality, we know that the shear is not constant distribution along the section. So we need a correction factor, and it's a rho 3.3 what's introduced in the software. So that will fix the issue that we assume the first order warping function. But now it's great, we can apply to any beam, and it's also applicable to the closed section. And the good side is this is fully compatible with the classical Timoshenko beam. So it's like basically if you apply to any beam, there's no any harm can be done. So you get exactly the same results as with the 6 degrees of freedom beam model. So it's a really handy. And what happens with this general degree of freedom, the warping is more realistic because of the shear deformations. It's a compatible, and also we're using shape functions like with the classical FEs. So it's even if you have just few finite elements in your beam model, it's really accurate. And we can use it in the stability and eigenfrequency calculation. And here is the example that we can also use those 7 degree of freedom beam models as a ribs of if you have like a wall or something and you have ribs, you can use 7 degree of freedom beam models. And now the rotational vibration modes are more realistic, and also you can calculate stability of these ribs if you're using this. But that's basically our theory, and now we discuss how to use FEM-Design. So I give few practical examples how you can apply this theory and tips how to use it. First of all, how to turn it on. So let's go back to this problem what we had it in the start. So the deformations of the classical beam model is 34 millimeters, and they should be like 11 millimeters. We know that this one is correct. Okay, and the stress distribution should look something like this. So how we turn on? We can go in any model and with any beam in the any model and just click over the beam here, and we go to the general tab of the beam properties, and we just turn it on. And because it's compatible with the classical beam models what we have in our model, it's nothing harm can be done if you turn it on. Then there's a few other properties. So first of all, because we have a warping, we also had to set how this beam is coupled in this end and thus this end, and we have one new degree of freedom what we have to define. This is V here, and we have to define V in the beginning and in the end of the beam. So it's we have to set, and of course we can build these library items as before. So you can give it name like fixed warping or released warping. So basically it means can the flanges move in the beam direction in here, or can flanges move like beam length axis direction in the support. And it means that both flanges has to be fixed. It doesn't, it's not enough that you just fix one flange, because then it's not warping support, as you learn later. Then we can solve this unsymmetrical dilemma. We can set the exact location of the beam with the bounding rectangle, or set like coordinates where you attach this beam to the surrounding structure. And then in the supports, we also have a new property. All the supports now have a new spring value, and this is a warping spring. So what is the spring value? What prevents the bending of the flanges in the support? And if we turn on the 7 degree of freedom model, you can see that the deformations, they were 30 millimeters. Now they are like roughly 12 millimeters, as they should be. And we have set the fixed warping support here because we have a really thick flange and really thick bolts. So it's fixed to the surrounding structure. So now it's set up. So basically you just turn on the model in the beam and set how the beam is coupled in one end with the warping, how warping is connected to the other end, and then it should work. And if you want to see more exact diagrams, you can add finite elements in the middle. And now we can also match the stresses of this solid model pretty closely. And in the cross-section properties, we now have the warping coefficient. It's here. And if you want to hand calculate it, but bear in mind this is only working for I-beams. And it's never exactly you see that there's a 2% difference, because now we are using much more complex theory to describe warping. So also the web is carrying the warping, because the web also bends and shears in the warping stress state. But roughly for the I-beams, this is like really easy hand calculation formula. Just calculate the bending stiffness of the flanges and multiply with the height and divide it by 2. And this is the St. Venant stiffness of beam models. It's here. And handy thing is that it works with any section. So if you go to the FEM-Design section editor and let's draw something like, you can use any shape, like even some crazy like this one. And then you just click calculate in the section editor. The warping stiffness will be calculated automatically here. But also those really hard to calculate correction factors for shear, those raw factors, they are also calculated here. And if you are dissatisfied with something, you can always double click on here and then modify it yourself if you are not satisfied with the warping stiffness. And in the result side of our software, there's now the torsion part is divided to two. So empty SV tells you how much the Saint Venant is carrying the torsion, and empty W or omega is telling you how much actually the warping is carrying, or the flange bending is carrying the torsion. And empty total means that total, if you sum up these two, might be plus and minus together, then you get this total external torsion of section. Then you have a by moment, and the definition was the flange bending divided by height. But if you have a complex section, like you don't have like flanges like I-beam, then it's something else. It's like divided to all of those beam fibers. And in the stress analysis, it's now handy. We can see, like if you click B, you can see the effect of by moment. If you click empty W or omega, we can see the shear effect of warping. And then we can look those classical or combination of these. If you turn on everything, then we can see the total stress state. So you can really dissect what is causing the stresses in the beam. Okay, let's look at other properties which we have. Maybe we want to calculate the stability of this system, and we know that the buckling shape is something like this. The critical factors are here. So now we have to set also for the loads. We have to, in 7 degrees of freedom, we have to manipulate the loads a bit. First of all, we have to set those where the warping is fixed. Like we imagine that this beam continues here, so we set fixed warping support, and we have to set the height of the loading here. The load height is here. Okay. And higher we set the load, the lower the buckling mode in buckling analysis will be. So the height of the load will decrease the stability, and that happens only in 7 degrees of freedom beam models. So for the stability analysis, the height of the load. So it's a property of the load in this new version, and we also can set the location of the load sideways. So we can also move the load sideways. So we can set the beam location correctly and the load location correctly. Just check your local system. So what is plus side and what is minus side when you set those loads. And now you get the right torsional and warping effects for these nasty double or unsymmetrical sections. And you do no longer have this dilemma of load located in the two places simultaneously. So it's and if you look those stability modes, now we get those lateral torsional buckling modes, or mostly it's like torsional buckling, or because this is a timber section and the Venant is really high. Okay, what about the support? Those are like becomes a bit more complex when you are using 7 degrees of freedom. So if we arrange the plates in steel, or it can be aluminium or concrete, it doesn't matter basically. The idea is that if we prevent the movement of the flanges here, but if you think all of those degrees of freedom, does this prevent the tension of the beam? Absolutely not. It will go through. What about the bending in vertical direction? Well, that probably goes through this coupling, and same applies to secondary bending. But if you think about twist, okay, the twist will go through, but this is actually warping support. So this is only preventing the movement of the flanges. So we have to model this somehow in our finite element model. So we have to introduce a warping support. So this combination of plates will prevent almost totally the movement of the flanges to opposite direction. So how to do it in FEM-Design? First of all, I just tested or showed how it works. So this is a shell model, and then we just integrate the top flange bending moments. So they will look like this. And if we do 7 degrees of freedom beam model, we set the warping support here, and warping only support in the middle of the beam. So this is a support when there's only this warping spring is really high, or almost like high value there, and you can see that it matches pretty well with the shell model. So we just set the warping spring. All the other degrees of freedom we set to 0 because all the others go through, but this is a warping support. And if you remember that the by moment is flange bending multiplied by the height of the beam, we can see that those matches really well. So the shell model and the beam model will give you like same solution. What about this case? So now it's the weakness or coupling spring between the flanges are much weaker, and now we have to use semi-rigid warping support in this case to model this one. I didn't calculate it, so you have to calculate yourself. So please do not copy these numbers. I noticed that if I say some number, people usually copy it, but please calculate the number yourself what this is. And you can use any reference to calculate these but there's existing in the internet already these few formulas where you can calculate it. I just give you one example, so this is the easiest formula to use. So this will give you the warping stiffness of this web stiffness. So this will increase the lateral buckling capacity of the beam or prevent partly the torsion of the beam. And usually this is radians or unitless. So in FEM-Design, the default unit for warping spring is per degree. So you have to go to the settings of software and go to the radians or convert yourself to the per degree if you want to use it directly. So yeah, you can see the unit of the spring. So use some conversions or change the radians to put it in the software. And the final concept, this is like really starting to be like high-tech topic, but you have to know these things when you start to use warping models. So that's why I give you like introduction to this warping transmission. So with the classical beam degrees of freedom, like we think that this is a vertical bending of the beam, how it transmits from beam to column, it's really clear because the bending y of the column is probably also like a bending to the strong axis of column, so they are like linked together. So we can automate the transmission. And here, same, if we twist the beam, we can convert to the secondary bending of the column, and it's almost like we can just write the translation, or we can automate it in finite element software. So the transformation can be automated in first 1 to 6 degrees of freedom. And the only thing we have to worry about is the stiffness of the connection. So we just think that maybe it's pinned or is rigid or semi-rigid, but that's like only worry with the first 6 degrees of freedom. But if we go to the warping, it's not so clear what happens in those beam connections. But I can take you a few examples on how they should be modeled. So let's first discuss about the cases when the flanges are in the same plane. So, and if you see there's a small gap between the flanges here in this model, so there's a gap, so it means that the flanges of the beams are not connected. And then we do small cell model and see what happens. If we twist the main member or the secondary member, we can see that the main member, there's hardly any warping there and no rotation. So right way to model it in FEM-Design is to set free warping here. So you go to the beam properties and set the warping spring to 0 in the end of the beam. So it's like this. Just put the 0 here in the warping spring of the beam end property. What about this if we weld those flanges together, or we do some bolt flange, or really like put really high stiffness to the connection of the flanges together? What happens then? Now if we twist the secondary member, we can see that the main member also twists. So we can see that almost all of the twist of the secondary member transmits to the main member. And the bi moment is, if you sum these bi moments together, they match perfectly. So this is how you do fixed warping. So you just define fixed warping here, and then this is like probably good enough to describe this kind of system. So if there's a high bending connection to the flanges together in the plane, then we have a case when you have a lot of stiffness. So you have stiffness this way, and you probably know that, okay, there's nothing happened. The main member just bends down. There's not any twist. So it's like basically like this, that you have a fixed warping support in the connection. So probably the best way, roughly, to model this is that you put the warping support, what only prevents the warping here, and then it probably models it correctly enough. Or if you have only flanges, maybe you can calculate the flange stiffness. So what about this case, that you have different height beams? So you have a really high main member and really low secondary member. And Now if we twist it, there's hardly anything happening in the main member. And the reason is that only the top flange is connected, so the bi moment, which is like two bending moments on the flanges, cannot transmit. So probably it's better to model it as a free warping, so the lateral torsional capacity of this beam is not too high. So very minor warping in the main member. Now it's getting more complex if you have a like 90-degree corner. Yeah. So you have a twist of the main member, and if you observe what happens in the lower end of the column, so we have exactly the same bending, same direction in the top, but the model on the left twist clockwise and model on the right twist anti-clockwise. So it depends how you arrange the stiffness in the corner, how the warping transmits. And we can see that also only part of the warping is transmitted to the column. And this is really hard to calculate, but how you can think it in reality, okay, maybe you can think that there's this stiffness which will dissipate part of the warping. But if you want to be practical, but let's say how first, or think how we can flip the bi moment. So by applying negative spring value in the beam end, the bi moment will flip and the warping direction will flip. So it's like really illogical, because negative spring value in the beam connection in the first classical 1 to 6 degrees of freedom doesn't mean anything. But with the warping, it makes perfect sense that you can have negative value as a spring coupling between the elements. So if you have this arrangement of the stiffness, you probably set it as a positive spring value, and this you set as a negative spring value. So this is how you can describe it. And if you don't have any coupling between the flanges, probably it's easier to assume that it's free warping. But these are really hard to calculate, so you can always use safe side assumptions. So if you're designing the column, it's better to assume larger transmission. And if you design lateral buckling capacity of the beam, you can think as a weaker transmission and calculate both cases, and you're always on the safe side. And of course, if you have a lot of stiffness, maybe it's better to assume that its warping is fixed on the beam connection, so the warping cannot transmit. So, in the end, I give you a small summary. So you can think warping is everywhere. When there's a torsion, there's a warping. So you just have to. Now you understand that it happens. So it can be found everywhere, every structure, every material, and almost every section. And FEM-Design offers really good model because we have a general model, so it can be used in almost everywhere where there's a warping. And the new upcoming Eurocode will be more specific about the warping. So in new Eurocode, there's a bi moment B in the design formula. So actually, you have to get the bi moment somewhere in the complex situations. Finite element model with the bi moments or 7 degree of freedom is the way to get the bi moments out of the system. And then you have to understand, we will discuss this later, but warping does not solve all of your stability issues, because there's always like local stability issues in beam, and this only solves like torsional distortion of cross section, but not like other type of distortions of cross section. So it only helps in lateral stability problems of beams, but there's still like local buckling and distortional modes of cross sections what it doesn't handle. So there's a limitations as whole theory, and then you can also have more degrees of freedom in B model, not just 7. There's more degrees of freedom above the 7. But basically 7 degree of freedom is like the sweet spot where you can end, and after that the B models get so complex that it doesn't make any sense. And maybe if warping like feels a bit hard, it's just because we have used like usually in school we use like classical beam theory, and we have used so much those like 6 degrees of freedom beam formulas and classical bending moment shapes that it's because we haven't used it before. That's why it might feel like bit hard. But basically, it's not that complex thing. What happens? It's just like fixing of beam model. And if you look the existing Eurocode, it also there. It tells you that you have to take the warping into account, but it's not as specific as the new version of Eurocode. So I think that was all. It was a lot of things, and I'm planning to have a second webinar about this topic because there's a lot of probably like lot of like practical tips are needed to use this feature. And this is if you already have a steel design license, you can use it. So almost all of the FEM-Design clients get this, and I've been told that also like you can do like a one beam with the warping even without any steel license. So the version will be released like in probably within 2 weeks. So like I don't know, somewhere in the February 2026. So you get this feature in the use. But I will quickly check if there's any questions. But if not, then I think I can end the session. But I thank you all and have a nice day.